So good afternoon. My name is Ralph Wittig. I'm in the technology office at Xilinx, and I was asked to present on AI activities going on by Xilinx in the FPGA space. And we also have coming next year a new platform architecture, which is the first architecture optimized for AI processing on FPGA. So far, we're just doing emulated processing, if you want. The next generation ACAP device is really natively optimized for AI processing. There is a clicker. Nope, there isn't. There isn't one over here, no? We can do the remote click. Thank you. Appreciate that. Yeah. So a quick reminder, what is an FPGA? We actually build regular FPGAs that have just programmable logic, but we also build SoC FPGAs. This is a device called MPSC, multi-processor SoC. It has, first of all, it looks just like the devices that previous speakers talked about, CPU, GPU. I'm not showing the GPU. We have a GPU in here as well. It's not broadly programmable. It's an older generation GPU. But we have an SoC subsystem, which we call the processing system, consisting of ARM cores, A57 in the current generation, RPUs, Cortex R cores. We have on-chip memory, and we have MMUs, virtualized everything. We also really have dedicated I/O controllers and interfaces. And then we have the programmable logic fabric, which is really what the FPGA is about. Right? That's where we differentiate. The software programmable subsystems are non-differentiating. They're really just there to get mainstream software subsystems, essentially everything that Linaro stands for, up onto our platform, and then we differentiate with the FPGA itself. So I wanted to now talk about not CPU and GPU, because that's been well covered. I wanted to talk about a category that we internally call DPU, Deep Learning Processing Unit, and distinguish between soft DPUs and hard DPUs. Right? So DPUs tend to be these arrays of matrix multiply elements, typically two-dimensional systolic arrays. Google builds it in hard form, TPU. There's a bunch of startups out there, list some names. I would like to also point out ARM has Marvin coming as an IP. It was presented at Hot Chips a few weeks ago, so you can look that up. We build DPUs as soft overlays on our programmable logic fabric, and we have different DPUs. Xilinx actually acquired a company recently, DeePhi. We also have a processor effort that we've launched already on Amazon F1, so that's the FPGA in the cloud. This XDNN processor is running there already. So there's different soft DPUs. And these soft DPUs are really important because we can specialize them. Right? They are fundamentally 2D systolic arrays. And we take a network and we schedule layer by layer over this array. So we run in time, sequentially, parallel within a block, but in time through the blocks that make up the network. These DPUs can be specialized. Microsoft has done an extreme specialization where they take a network and they place each layer of a network on a different FPGA. And they reserve as many FPGAs in the cloud as the network has layers. Right? That means you don't have to store any parameters in off-chip memory. They fit into on-chip memory everywhere. And think about how fast that is. Right? So that's an extreme specialization. We have a framework we call FIN, which actually is available as an open source project. You can actually get yourself one of the 96 boards. The Ultra 96 board is actually on display out here by the colleagues out here on the booth. And you can see what that board looks like. We run FIN on there. FIN is an extreme form of a specialized DPU. FIN is, if you want, there's no pointer, right? So FIN is more what I call a synchronous data flow on the right-hand side, where we pretty much have taken the network and we've built a custom implementation of each operator of each layer, right? And the layer n-1 feeds straight into layer n. There's a feed-forward data flow without any intermediate buffering. Right? So the production and consumption rates of each layer are perfectly matched. There's no intermediate storage. Think about how efficient that is, because that's the energy goes into the memory, as one of you guys just pointed out right now. Right? So it's all compute. There's no buffering. So that's synchronous data flow, fully unrolled. We can also do more folded, and that's basically the general So the architecture on the left, which is more folded, and then we sequence the layers of a network in time. Right? And of course, there's a broad range of options in that we can go anywhere from fully unrolled to fully sequential and anything in between. Right? And we could be building 2 cores or 3 cores, and they're all different specialized. Some have more precision, some have less precision. Right? This is the customization that you can do with an FPGA. That's what we exploit over here. And so we further distinguish between what we call overlay processors, which are essentially DPUs that have an instruction set. And so a compiler, like we talked about over here, can target. We've also built operator libraries, which we then synthesize and place and route to the FPGA, which really amounts more like to a native execution natively on the FPGA. But the taking the operators and compiling them straight onto the FPGA really involves place and route, which is anything but JIT. Place and route is several hours, right? Whereas on the left-hand side, you customize your overlay processor, put it into the bit stream. Once you build that over there, then you can JIT compile to the overlay processor. Right? And so you can get the best of both worlds of customization at the same time fast compile time. So that's an overview of DPU spectrum. Right? Now, what do we do with this? Actually, yeah, so a plug for our products over here. XDNN we run in the cloud at Amazon. We have from DeePhi coming in 2 different DPUs, Aristotle and Descartes. Aristotle is more CNN focused, Descartes is more LSTM focused, so you can specialize even amongst the different types of neural networks. And then we have our FIN package, and you can sort of see the GitHub links for all of these, where you find these processors. And the slides are, my understanding is slides are available after the talk as well. So looking at FIN, what we can do over here is we can take a network, train it, and then we can optimize it for reduced precision. Right? And so what you do is you start out with a network, let's say ResNet, well-known network. Floating point baseline is trained, and then we jump straight to an 8-bit, so 8 bits means activation bits and wait bits. That's so 8 bits. We jump from floating point to 8 bits, without retraining. We don't have any change in error. The error rate doesn't go up or the accuracy doesn't go down. Right? So then we go and further quantize to a 4-bit, 6 bits. 4-bit wait, 6-bit activation. Now you see the error going up. We've lost some of the precision. Not a problem. We basically just retrain it and we recover all that accuracy. And it can keep going. 3 bits, 5 bits. Right? Retrain, recover the accuracy. Right? And we can keep going all the way to 1-bit, 2-bit. Think about it. Well, we have a 1-bit or ternary wait and a 2-bit activation, and we see only a less than 5% change in accuracy versus the floating point baseline. Think about how much less work you're doing over there, how much more compact this is, lower energy, much more throughput. Right? This is the spectrum that the field hasn't really explored all that much. That's what you can do with an FPGA. But we need to make the frameworks and the compilers and the library sets aware of these really reduced precision formats. Right? If you think reduced precision means 8 bits, that's not reduced precision. We start at 8 bits on the FPGA. Right? Reduced precision is anywhere of 8 bits down to 1 bit. Right? So we need to think about quantized data types, quantization formats, and there's a lot of detail here with how you need to quantize, because you lose a lot of precision, and you have to really do this during training. So taking a network, training it, exporting it into Onyx and whatever not, and then just implementing is not enough. We need to have the data path of the architecture really represented during training. Right? The field hasn't even thought about that yet. Right? So moving on, so you can sort of see there's a spectrum for the same network. We can run it anywhere from floating point to 1 bit. There's an accuracy trade-off, but it's really a hardware cost trade-off, right? And it depends on how much accuracy you actually need in a network. And you can choose how much hardware you want to spend on that. So this is a very interesting space. Now, do any of the frameworks support this kind of trade-off? No, they don't. Right? So there's a big gap over here. We're struggling with that. We can demonstrate this with hacked up frameworks. We're open sourced our environment for doing this, FIN, but we need to really get this into more of the mainstream frameworks. So we also have the more instruction set-based overlays. This is the block diagram of the DeePhi DPU. You can sort of see there's a complex computing array, number of PCs, processing elements in the middle. These are all MAC units, right? And then we have on-chip memory with spill restore, fetchers, controllers, and so on. These are soft cores that are synthesized into the FPGA. And these soft cores beat GPUs, performance-wise. This actually beats NVIDIA, right? You think like emulated on an FPGA is not as good? No, this actually is very good, right? Because what you're doing over is you're specializing the interconnect in the memory subsystem. It's not about the compute. It's about the clever use of on-chip memory. And that's what you can do with these architectures. And then you have standard instruction set. So these architectures are easily targetable from the usual frameworks, whether that's, conversation with ARM, ARM&N should be plugging over there, TVM should be plugging over there. So the compiler we've built so far is actually based on TVM, and we'd like to really explore, contributing back some of the stuff that we've built for DeePhi DPU. It's configurable anywhere from, so the pre-built options are 1,000 DSPs or MAC units to 1152 MAC units to 4,000 MAC units. And then we can fit into really small chips. And these small chips are like 1 watt, 2 watt, all the way to larger chips, which are more like 5, 10 watts. And we put this in the data center, we're running chips that are 100 watts plus. Right? So it's a spectrum of options. And that's what you get with an FPGA. So we have a tool suite or software stack. It's this pruning and quantization technology that I talked about that's in here. Then we've got the network compiler and assembler, and then the runtime. I don't need to go into a lot of details. You understand what these technologies are. We've heard enough talks. The only question really for us is, does Xilinx have to build this, or can this just be supported by the community? Right? So that's a discussion we'd like to have. Right? This is not necessarily differentiating. Differentiating are the architectures, and of course the fabrics, meaning the FPGA fabric, on top of which we build these architectures. That's what's differentiating to us. Right? So do the tools have to be differentiating? Well, they have to be differentiating in that they have to support this extreme form of pruning and quantization that we can support with an FPGA. So prune, fine-tune, quantize, and further fine-tune. That's really the flow. When you do this, you can sort of see a baseline network unpruned. So this is basically parameter compression or weight compression. Unpruned, you get some kind of performance. This is a simple network, SSD. It's actually a fat network, to give you an extreme example, on a small image size. This is the framework we achieve at the different chip sizes. So 7020 Zinc is a really small chip. ZU9 MPSoC is a much larger chip. This is sort of the sub 10 watt spectrum. We go all the way up to 100 watts plus. Right? Get some frame rates, and then we start pruning. And with pruning, look at how much fewer parameters you have, which means you don't have to spill and restore as much. We don't have to fetch as many weights. We can really get our MAC units working all the time. And you get almost an order of magnitude more performance. Right? So if you don't prune your network, you're not doing yourself a good service. You need to prune networks. Right? And then furthermore, I said quantizing. Quantizing without retraining is pretty easy. You just pick you look at your distribution of activation values per layer, and you pick sort of a data format. Say I have 8 bits to spend, how many integer bits, how many fractional bits. It's pretty straightforward to select that. You just want to make sure that you don't spend too many integer bits. If you just have very small numbers, likewise you have really small numbers, you need to really have a lot of fractional bits. So we have tools that pick sort of this, how you spend your bits automatically. And these tools, without retraining, get very little loss in accuracy. If we want to go to less than 8 bits, we really have to get into retraining, and at that point in time, inference and training can't be separated anymore. Okay? So main point over here is that for 8 bits, for the mainstream networks, for image detection and so on, we don't even have to retrain. Just go from floating point straight, direct quantize to 8 bits. And then finally the runtime. The runtime is, as you would expect, so we have a host, whether that's an on-chip CPU, ARM cores, or external CPUs, ARM-based or Intel-based. Have a host somewhere, and we have our DPU, and the host really runs an OS, which has a driver for the DPU, and then we basically just hand off these compiled networks in DPU binaries to our DPU core, and the DPU core runs. Once an image is completed, control goes back to the host. Right? So pretty standard runtimes, also not very differentiating here. Now, it gets interesting when we have sort of more heterogeneous fabrics, where you have CPU, GPU, FPGA variants of DPUs. You might have a DSP, then these runtimes become a lot more interesting. Because then it's about optimizing, picking the right fabric for the right task. You can split a network across multiple engines. We don't do that yet. So this was MPSoC, right? So that's today's platform. So processing subsystem, SoC, ARM cores, A cores, and R-class cores. We also have a GPU in there. Then we have programmable logic and our IOs. Moving ahead, next generation is announced already. Next generation is known as ACAP. It's an accelerated compute platform over here. ACAP at a high level is announced. The actual device family is going to be announced in almost 2 weeks' time now, so early October at the Xilinx Developer Forum. It takes place in San Jose in California. If you happen to be around, please stop by. Over there, we're introducing this new fabric we call software programmable engines. So the FPGA is lookup tables, blockrams, and so on. It's very low-level hardware. You can build very small operators out of them. That's very good. But you still use programmable interconnect to tie all the stuff together. It's still very flexible. We can actually get more density and achieve more efficiency by going to more coarser-grained elements, and that's what these software PEs are. At a high level, so if you look at this array now, so this array in red, software programmable engine array, look at one block in there, one tile. It's actually an ISA-based vector processor. It's a vector VLIW. Vector length will disclose at developer forum, but it's a standard vector processor. It's VLIW, it has multiple concurrent units, load, store, compute, vector, and scalar. And it has local memory. And then it has interconnect. And so it's a coarse-grained FPGA, one might say, but it's really a processor-based building block now. So we have, build this out. So the local memory is multi-banked, where we basically allow bringing in new data sets to work on while you're working on the current values. And we ping-pong between buffers. And hence we really overlap compute and transfer. That's what really makes the FPGA efficient. And as I said, so this is the first time that Xilinx is actually optimizing any fabric for machine learning or AI. And this is the first time we've actually built custom units in there that are really driven by this application domain. Up to now, the FPGAs were really generic. They're already very good at AI. Now they get a lot better. And I'll give you a teaser. Fundamentally, for GoogleNet, we get a 20-fold increase in throughput at the same power. So at basically the same energy profile, we get a 20x increase in performance. Moore's law gives you not even 2x anymore, slightly less than 2x. So the difference between an optimized architecture and a non-optimized architecture is essentially an order of magnitude. Right? And this is not even a hardened core. This is still a more generic fabric, and we build overlays on top of that still. So that's one tile. Data movers in there as well. I'll get to that. This is now an array, so we build an array of tiles. And the memories are distributed because you want the data where you're going to be consuming it. And this is a distributed memory where a single core can only see the memory that's immediately around it in adjacent tiles, but you can't see memory that's multiple tiles away. So it's not a shared memory architecture. It's a very locally shared domain, but it's overall really distributed segmented memory space. Right? So it's a very different kind of a multi-core. I'm not sure if you want to call this a multi-core. And why have we done that? We fundamentally focused on deterministic performance and lowest latency. Right? So latency goes up with buffering. Minimize the buffering. Non-deterministic behavior comes from caches. Don't implement caches. There's no caches over here. Right? This is a very different kind of an architecture. It's sort of an FPGA, not built out of lookup tables, but an FPGA built out of processors. That's what this really is. Of course, we still have FPGA in there because there's still operations which are not vectorizable. They're not data parallel. And we use the programmable logic for that. The programmable logic is also very good at building different memory hierarchies. That's what we use the FPGA fabric for. I'll get back to that in a second. So one core can see the memories of adjacent tiles as well as its own tile. And then you can build things like, might have 3 cores operating, each running a program. One produces something, hands over to the next core through shared memory pointers. You could have 1 core running a convolution, the next core running a pooling operation, the 3rd core running an activation function, right? And they're all running concurrently in a pipeline and overlapping and just handing off data. Data handoff is all done locally. Data doesn't move very far. It's very energy efficient, right? You could also get yourself in the situation where you run out of memory in a certain vicinity. I need to push this further apart, and then I need to go to a remote memory. And then we just put our interconnect in over there. It's a dedicated circuit we set up. The circuit is actually JIT compiled. So if you think sort of this is place and route, it's sort of place and route, but it's really fast, right? So this place and route runs in seconds. That's why I say it's not really place and route anymore over here. So that's also new. And then, of course, important patterns like multicast are supported as well, because you might want to sort of say, if I parallelize an operation, where I take sort of a convolution and I split it across multiple cores, they will all want the same weights, the same parameters. They will run on different activation values, but they want the same parameters. And so I can do broadcasting of weights and then individual in parallel attack the activations. So different patterns in here. I don't have a complete list in this diagram. So then building this out, how do we, so this software engine is not something we natively compile networks to. We could, fin style, but we really plan to build overlay processors, DPU overlays for this one again. And over here you have the heavy compute operations, like the conf and the FC fully connected layers all mapped to the software programmable engine. And then we build sort of custom memory hierarchies for different tensor stores and also tensor reshape operations into the programmable logic, because that's where you really need the bit level access. So that's a preview of what these overlays will look like for the ACAP generation. So I sort of mentioned this already. When we run GoogleNet, we'll have a lot more detail on this one. GoogleNet is an example of other networks running as well. We get a 20x increase in throughput versus our current generation devices, right? And of course, significant power reduction too. So overall, this architecture becomes a lot more software programmable, which makes it a lot easier for this community here to support our devices now. We significantly increase the efficiency. FPGAs already, if you can use them, better than GPUs. Now they become more usable because they're more software programmable, and we get a huge jump in efficiency, right? And the key sort of aspect is that we found, single core scaling ended. People went to multi-core. Multi-core tends to be tree-style memory hierarchy. Each core has its own cache, and then there's some cores that share an L2 cache, and then some more cores share an L3 cache. These tend to be sort of tree-style memory hierarchies. We don't build memory hierarchies like we let you customize the memory hierarchy. And we really, by doing so, minimize the data movement. And that's what you have to do these days, because this is fundamentally, in the end, energy constrained, these problems. And AI is really just a big use of compute. And if you're not energy efficient, you don't stand a chance, right? So summing up over here, we had before software programmable processing subsystem already, application processors, real-time processors, GPUs, all ARM licensed IPs, non-differentiating, differentiating programmable logic, but more of a hardware design flow. Now we're adding these software programmable engines, and we still have a hardware adaptable but JIT compilable interconnect and memory subsystem in there. And that's the summary. And now, this is what I really came here for. I want to have conversations about topics on things we need to work on together. So we see many problems. I think it's just exciting times. It's a finally change and faster movement in this field of computer science again. On the left-hand side, training for compression, right? So it's not enough to train a network in floating point, then snapshot it, Onyx or other handoff, and then just map it and implement it. You need to retrain your network, and probably multiple times, as you go towards more compressed and more reduced precision, right? And this retraining is an iterative process. We don't actually take a network from floating point to 1 bit in one step. We take floating point, we quantize to 8 bits, we retrain, recover accuracy, then we quantize more, 8 bits and 4 bits, quantize, retrain some more, then we take maybe the activations to 4 bits as well, then we're at 4 and 4. Successive retraining steps. It's a slow crawl. That's actually a really interesting search space problem. Right? These networks are it's very difficult, very easy to get stuck at a local optima, and then the network stops learning. Right? And so anyhow, so training with compression in mind is really, really important. And I didn't see that covered at all today. That's why we teed it up. Quantized operator libraries. So we need to have modeling libraries for simulation, but really also for the training phase of what do these really sparse data paths look like. And we have to be data path detail aware. Typically, the quantizer block is really important. And we also have to be pipeline aware in terms of what does the data movement look like, because you have to be aware of that for training as well. And then exchange formats. So we still scratch our heads. How universal are these exchange formats really? We still see data scientists cook up new networks. And I can't remember who gave the whole depth-wise separable mobile net. And so it's actually good details shown earlier today. New networks pop up that have new operators. Oh, and then a framework can't support it. Oh, and then the data scientists just cook up another framework. Right? And it's continuous. Right? And so I asked how universal are these current Onyx, Kronos has NNEF, there's probably some other ones I'm not aware of. How universal are these exchange formats? These are in catch-up mode. Will they ever be caught up? Right? So this requires data scientists, some discipline to actually work with these framework providers, exchange format providers. I don't know, the community has to come together. Right-hand side, network compilation and optimization. There's clearly and I think the TVM really talks about that out well. There is I think it was called NNVM. So there's a processor or implementation independent optimization. That's graph optimizations and so on. And then there's a processor dependent optimization, which typically is more about memory spaces and so on. And so fusion, tiling, and things like that. So we think that can be standardized because that's common across the board, right? And that's what we see this coming up in what Rob presented earlier today. The Amazon presenter and TVM presenters really pointed out how TVM does that as well. So I think there's good collaboration opportunities there, right? We built our own compiler right now, but we don't think we need to do that in the mid to long term. Runtime and scheduling, very exciting. Heterogeneous platforms, that's what it's all about. You can sort of see, it's CPU plus accelerator mix, but it could be actually multiple fabrics working together, right? I didn't see enough talk about multi-tenancy and virtualization, and then did I even dare to bring up security, right? So I didn't see much talk about that. But if we can get going with standardizing on heterogeneous runtimes and dispatch and hardware accelerated dispatch and coordination, that would be very useful. And then finally, we are scratching our heads, are these DPU architectures differentiating for Xilinx, or are they not? Could we even open source them? Could we contribute them to the community? We've taken our operator library, our native, compiled to native operator library, the Fin framework, we've open sourced that. Should we be open sourcing the DPUs we've built? I don't know, it's a discussion we're still ongoing inside of the company. So that's just some topics. We'd love to hear from you. How can we help? How can we contribute? What problems are you facing? Thanks for your time. I'll take a few questions.
Hi. With respect to retraining for reduced precision, how are you doing that in the backprop? Because traditionally, a lot of the literature is when you're retraining with quantized values, it causes the gradients to explode.
It does, yeah. So what we do is we truly take frameworks. What are they? They're really just operators. They have forward path operators, backprop operators, and we basically take those operators, and they're typically just expressed as C code, right, which you can run on any CPU, and we just change that C code. And we basically put in the effects of quantization. So within floating point, I can model quantized numbers. I can say my floating point value can only take on certain discrete values, right? And so within a floating point data type, I model the effects of quantization. And so I have to change my operator library to be quantization aware. And we've done that. We've done it for Torch. We've done it for PyTorch. We've done it for TensorFlow. They're all slightly different, right? It drives us crazy. The same techniques, but we have to then rewrite all these libraries for the different frameworks, right? Can we standardize on these libraries, right? There isn't much magic. But fundamentally, it's emulating the effects of discretization within a floating point container. That's what we do.
Yeah, there's a package called Ristretto that was used in Caffe that did exactly that.
For example, right? And if you look at Fin just takes that multiple steps further. Thanks for the question.
Thank you. So I just want to follow up the last question. So does the retraining works for all the models, or it just works for? So yeah.
Yeah, it's very interesting, right? There used to be sort of common held belief inside the company until fairly recently that take any network to 8 bits, right? And typically, as you saw in the chart I showed, train in floating point, quantize to 8 bits, don't even have to retrain. Accuracy loss is like less than 1%, not a problem, right? That tends to be true for ImageNet type problems, right? Try that on other problems and data sets, and it doesn't work anymore. It really falls apart. There's actually some problems we can't even quantize and retrain to 8 bits. They don't even converge for 8 bits, right? And there's some other ones that we take into, I don't know, 2-bit activation ternary weights. It's really, it's network and cost functions or problem statement and data set dependent. You cannot generalize that, right? Look at the Hot Chips machine learning tutorial. There was actually a section on training in there, and there was actually an interesting chart shown. Like if all networks were easy to train, they just looked like a bowl surface like that. In any way you crawl during training, right, your error only goes lower because the bowl, your little marble just finds the minimum. There's an easy to find. And then real networks have a search space that looks more like the Grand Canyon with all kinds of like plateaus, side canyons, mesas. You get stuck in a gully, you can never climb out of it. Right? We find though that networks that are in the market right now are just way too fat still. You can really trim them out. Parameters can be compressed, even like edges can be cut out, and they still work. Right? But you have to do this in a very successive and iterative way. You cannot go from like, floating point 1 bits or cutting out all parameters. It doesn't, you have iteratively and search, and it's not easy to do. There's much more to come here.
Yeah, got it, thank you. So another question is that, because you mentioned TVM, so I'm also working on TVM, so I'm curious about at which level of the whole compiler stack are you using TVM? Is it get directly to the ISA or something else? No,
we tend to always do sort of what we first do is we basically look at where we can fuse together. We have basically on-chip memories. I could go back to the block diagram, but let me try to just abstract that. So we essentially bring in the first input tensor, and then we run from there through our systolic array of max. We fuse on there the activation functions, the pooling. That's just done inline, right? And we don't go back to a storage for these inline pipeline operators, right? So you right away fuse multiple network graph nodes together into a fat node, right? So, and that is pretty universal. That's abstract, right? But then you have to look at how many MAC units do I have in there that determines how big of a tile you can build, that you can run data parallel within a tile, but then have to sequence over that array multiple times till it finishes the compute for a given layer. Right? So there's a portion that's fairly DPU configuration independent, and then there's a portion that is actually very dependent on the DPU configuration. I don't know does that answer your question? Maybe.
Yeah. Thank you.
Okay. Thank you.
Okay, thank you very much. It was really interesting.
Thank you for your time. I'll be around so you can come talk to me offline as well.